Welcome, everybody. It's wonderful to have you back, and we're excited about this this term coming up. We have one of our own faculty affiliates, Nicolas Papernot, to speak today about what does it mean for machine learning to be trustworthy. All of us should know Nicolas by now, but just to remind you, he is an assistant professor in the Department of Electrical and Computer Engineering and the Department of Computer Science here at U of T, and a faculty member at the Vector Institute, where he holds a Canada CFAR AI chair. And his interests in research are across security and privacy, in machine learning. He's a Connaught researcher and previously a Google PhD fellow. So I think we should also know that he is the co-author of Clever Hans and TensorFlow Privacy, two open source libraries widely adopted in the technical community for benchmarking security and privacy. And before coming to U of T, he was a research scientist at Google Brain. Is that everything, Nicolas? Is that all the exciting news people need to know about you? Okay, now we really want to know this very important question.
Thank you for pronouncing my name perfectly.
Oh, wonderful. Okay, right. Everybody heard it. There we go. Okay, Nicolas, take it away.
Thank you. Thank you for the introduction, Jillian. So I'm very excited to present our work today. I just want to let you know before I get started that, of course, this is not work that I did on my own. It involves a lot of collaborators and also recently some of my students. So I tried to put the title of the papers at the bottom of slides so that you can reverse look up who is involved in the different projects. So what do I mean by trustworthy machine learning? I just wanted to take a couple of minutes before I dive into the research itself. And it really means anytime that you're trying to allow humans to trust the machine learning systems that you're deploying. And so I'm going to give a couple of examples of the different aspects of what I call trustworthy machine learning that I'm going to discuss today in the talk. The first one is really the security. So here, what you have is an adversary that is actively trying to manipulate the system that you've deployed. So on the left, I've showed an example, which I guess is timely now, again, where this is an example of what happens when you have the ability to manipulate the training data of a machine learning system. So a couple of years back, Microsoft released a chatbot that was basically interacting with Twitter users and learning from its interactions how to produce tweets. And so what people really quickly noticed, I think it took less than 24 hours, is they could use that ability to poison the data set of what is essentially a language model. And they forced the model to learn how to produce what is essentially racist content. And so this is an example of what the model eventually produced as a tweet here on the left, which I should say is one of the few examples that I was comfortable putting on my slides. So you can unfortunately find much worse examples online. And given sort of the recent political events, you can sort of understand the implications of these attacks. And then there's also a wide range of attacks at test time once the model is deployed, where here the idea is that the adversary will exploit sort of the large error surface that machine learning models typically have because they cannot learn how to make the correct prediction on all of the possible inputs that you're going to show them at test time once they're deployed. And so here, this is sort of another unfortunate example where YouTube uses some machine learning to filter out videos that are not appropriate for children. And so some of the parents noticed that, for instance, this video was not being filtered out and still made it in the YouTube Kids app, despite sort of having violence in it because the car is about to run over the character. So this shows us that when you have a high dimensional input, as is the case with videos, it becomes very hard to have good generalization guarantees for machine learning systems. And so what this means is that the adversary can systematically exploit this error surface and find inputs that you're going to misclassify. But there sometimes does not even need to have an adversary involved in the picture. So this is where we shift from security to something that is more along the lines of safety, where the prime example here is really self-driving cars, where you might not have an adversary that is actively trying to force your car to crash, but there might be adverse environments in the sense that you have very subtle changes. Here is illustrated here with the changes of lighting in the input to the camera, which you haven't trained your system on. So this becomes sort of a worst case test input to your system. And you can see that originally the model is predicting that the car should follow the road and turn left. And so now with the picture here on the right that is a little darker, it's unable to predict the right trajectory, and instead the car would be sort of pushed outside the road. So this is an example of basically a problem that is related to what is going on here in the right, but this time without necessarily an adversary. We also work on questions that are related to the privacy of the training data, because when we train machine learning systems, very often we train them on data that is sensitive. So a prime example here is healthcare, where you're training models potentially on records that are from real patients. And so what we have to be concerned about is these training points leaking at test time. Once we've deployed the model, if people are able to query the model, they might learn information that they didn't know that was contained in the training set. And so here we, in my group, we've recently come up with a result where, for instance, if we're able to know what labels a machine learning system is predicting, then we can tell whether a particular point was used to train the model or not. And so you can imagine if, for instance, the model is trained on healthcare data, being part of the training set might already be something that is sensitive that you might not want to reveal to other people. And then the last aspect of the talk that I'm going to go through is really around the fairness and the ethical implications of using machine learning. So again, we've had a lot of coverage recently around the limitations of facial recognition, due both to the data, but also just the algorithms that we're using and the way that we're training the models. And in the very last couple of slides for the talk, I'm going to discuss sort of our work on deepfakes, where here this sort of begs the question of how do we think about the implications, the societal implications of the progress that we're making as researchers in the machine learning community. So in the first part of the talk, I'm going to look at the first two problems that I discussed in the introduction, which are security and privacy. And I'm going to show you how in these two research areas, we've taken very different approaches at understanding sort of what are the security implications on one end and what are the privacy implications. And as a consequence of this very different approach, we have very different outcomes, where in the case of security, we essentially have something that is still an open problem, where we do not know how to deploy a secure machine learning model. Whereas in the case of privacy, we've made significant progress. And so now we can actually deploy models with tangible privacy guarantees. And so I'm going to explain sort of what is the, what I think is the fundamental difference in the two approaches. So feel free to interrupt me for questions at any time. I'm just going to pause for a second. I have the chat open. If I see a question pop up, I'll stop for a second.
And also keep an eye on that for you, Nicolas.
Okay, thank you, Jillian. So before I sort of get into the details, I wanted to give a little bit of background on sort of what I'm going to discuss here in the first part on security, which is something called adversarial examples. So this is something that we discovered back in 2015, 2016, where what we found is that you can find inputs to machine learning systems that are consistently misclassified by these machine learning systems. So the idea is the following: is imagine that you have, in this example, the model is trying to recognize the digits that are in the image here. So this is sort of a very simple task that makes it easier to understand how the attack works. So you have this image here of a 1, which if you pass to this neural network here, is correctly classified as a 1. And so the goal of the adversary is to force this neural network to instead misclassify the image as a 4. So they've decided that they want the image to be misclassified as a 4. So one example you could think of is if I'm writing checks for someone, I could imagine perturbing the check that I'm writing in a way that the person will visually think this is still sort of a 1, but instead the computer would recognize the digit as, for instance, being a 0. And so it would give them sort of a smaller amount of money once they try to deposit the check. So this is sort of an example you can think of. And of course, depending on what the machine learning model is doing, the security implications are going to vary. So essentially, what happens to find the way that we should perturb the input is that we take a look at the neural network architecture, and we're going to compute the Jacobian matrix of this neural network. So what this means is we're going to compute the derivative of each of the output scores that the model is predicting with respect to each of the input features that we're providing the model, which means that we'll know when we change these input features, how is that going to impact each of the possible outputs that the model is making. And so, for instance, if we have a positive derivative, what this means is if we increase the input feature, the corresponding output score is also going to increase. So that tells us, as an adversary, how the different features are going to contribute to the goal that I'd like to achieve. So for instance, here, since we want to misclassify the image as a 4, we're going to look for features that have derivatives that are very positive with respect to the class 4, and negative or close to 0 for the other classes, which means that once we increase the pixel in the image, this is going to increase the score of the model in predicting the class 4, and it's going to decrease the score for the other classes. And so if we modify enough of these pixels, eventually the model's prediction will change. And so this is what we do here, where we're basically building a saliency map where the horizontal axis on the graph correspond to the layout of the image. So each of these squares here corresponds to one of the original pixels. And the vertical axis shows how much the feature is salient, so how much it contributes to the adversary's goal. So the higher it is, the more it contributes to the goal. And so for instance, here, I would perturb this pixel first and look at the change in the prediction of the model. And so if you repeat this process several times and you update sort of the Jacobian matrix and this saliency map at each iteration, and then you perturb 1 or 2 pixels, eventually you obtain images like this one, where once you present this image to the model, it will now misclassify it as containing the digit 4 instead of 1. So this is sort of surprising, and it can sound more like sort of a fun little experiment. But the problem for people deploying machine learning is that this is very systematic. So what we were surprised of at the time is that if we take an input from any class, so any digit, we can force the model to predict any class that we want. So we can force the model to recognize it as any arbitrary digit. So this is what you're seeing here on this confusion matrix, where all of the images on the diagonal are correctly classified by the model from 0 to 9. And all of the off-diagonal images are classified according to the label that is at the top of the column. So if you take the first row, for instance, this image of a 0 is then classified by the model as 1, 2, 3, 4, 5, and so on. So what this means is you can arbitrarily control what the model is predicting on any arbitrary input. So of course, this is not good in terms of the security of the model, because now you have no guarantees of sort of the integrity of the prediction. And so this is something that was initially sort of surfaced around deep neural networks, and especially deep neural networks that are working with vision data. But it's a problem that's pervasive across all of the machine learning approaches. If you've used things like logistic regression or nearest neighbors, they have sort of similar vulnerabilities, and you can adapt these algorithms to find similar inputs. You can also use this in very different applications outside of vision. So for instance, we've showed that you can attack malware detection using this. So when you're trying to detect malicious software, for instance, on smartphones like Android applications, you can modify these applications so that they still contain the malicious behavior, but they were misclassified by models that tried to detect malicious software as being benign. So you can evade the detection. Or another example is there is a lot of progress in reinforcement learning. For instance, you've probably seen sort of the videos online covering sort of the developments around agents that are playing video games. So what we can do here is perturb the background of the video game and an agent that had learned initially how to play the video game very well, that would, for instance, win against the game itself, would now take sort of the wrong actions because of the perturbations that we're introducing in the background. So this is sort of the concern that we had at that point, but we still had one question, is whether we can perform these attacks without having access to the internals of the model. So I see there's a question, so maybe let me pause for a second. Have you tried? Yes. So GANs are, so do these techniques work on GANs? Essentially, GANs are solving a different problem because they're trying to generate inputs rather than trying to classify them. But the architectures that they're using are also vulnerable to GANs. And so people have tried to use, for instance, the fact that you have access to the distribution when you're learning a GAN, or at least trying to get access to the distribution to detect adversarial examples, but so far this hasn't been successful. So unfortunately, there hasn't been sort of a class of models that we've been able to find that doesn't have this, this vulnerability. So the next part of our work looked at, do we need access to the internals of the model to be able to find these perturbations? Because in the work that I presented so far, you need to know the details of how the model makes predictions in order to find these inputs. So what was very surprising is that we figured out that you can essentially exploit access to the predictions of the model to reverse engineer the model. So once you have, for instance, a website that allows people to submit images and then you output the label that the model is predicting, then this allows the adversary to query your model and through this interaction to copy the model locally on their machine. And so what this means is now the adversary is able to reproduce the model that you have, which is a black box that you don't have access to the internals. They're able to reproduce this model locally on their machine. And so there they have complete access to its internals. And so once you've done that, essentially what you can do is you can attack your local model as an adversary and then submit the inputs that you find on this local copy of the model to the victim model, which is also going to misclassify them. So this has two consequences. The first one is that there are some serious IP questions that are raised here, because as soon as you're deploying a model with an API that reveals the predictions of the model, you should essentially assume that people have the ability to copy your model. And so you cannot sort of protect the IP of that model. It's very hard, sort of, there is probably no way we can defend against this, because as soon as you reveal sort of more and more points of a function, sort of mathematically, you can see how the function is easy to identify if you have enough points. And so here, we might be able to detect when people are doing this, but we certainly cannot prevent it. And then the second implication of this result is that now we do not need to have access to the model that we're trying to attack. So you could imagine, for instance, if I wanted to find adversarial examples for something like a Tesla, I could just present it with inputs and observe sort of, for instance, the traffic signs that it's recognizing on its dashboard. And through this continued interaction, I would be able to sort of reverse engineer the model that they've trained to recognize traffic signs, for instance. And so this is sort of, this makes these attacks sort of realistic in the sense that they don't need access to the underlying model. And so now the question is, how do we defend against those, right? So this is something of importance given the applications that we're using machine learning for. And unfortunately, sort of my first part of the talk is somewhat pessimistic because we haven't had any significant progress towards defending against these inputs. And let me try to explain to you why. So essentially what happens is that initially the observation we made is that we have training images, so examples of the behavior of the model we'd like to have. So here, for instance, we have this image of a 3. And the ideal decision boundary that we would like our model to learn is this solid black line. So we'd like the model to learn that beyond this line, images are of a different class, for instance, the class 5. And in practice, because we're learning from finite training data, we're learning a slightly different decision boundary. which is the red dotted line here. And you can observe that this decision boundary is very close from the training image. And so what this means is that it will be very easy to perturb the training image a little bit to push it on the other side of the decision boundary in between these two lines, where the model will essentially misclassify them. And so what we've done, sort of what the research community has done, is try to make the models less sensitive to small input perturbations. So basically training the model with an objective that requires that the model makes the same prediction within a vicinity of each of its training point. So you're saying if you have an image that is at a smaller at a small distance of one of your training images, then you should classify it with the same label than that training image is. Which makes sense to defend against these attacks that are introducing what to us as humans seem like small perturbations that don't affect our perception of the inputs. And so this is something that we've made
Nicolas?
progress. Yeah.
There's a question from Rania. Rania, do you want to just ask, or we could read it in the chat?
Yeah, you can just read it from the chat. I mean, it's like,
sure.
You mentioned to the adversarial examples, but it's like, my thought is like, we're using that adversarial example as a privacy protection to sharing, let's say, our image in a social media, for example. But at the same time, we wanted to protect the machine learning based systems from the spoofing this system. I mean, by using this adversarial. So how we can trade off between these two objectives?
Right. So this is a very good example. For instance, because it's hard to defend against adversarial examples, people have used them as a defense against sort of applications of machine learning that they do not want to be the victims of. So for instance, if you don't want Facebook to recognize people's faces in the photos that you upload, you can imagine applying an adversarial example, which is not going to affect how your friends perceive the image, because the perturbation is often very subtle and not visible to a human. But this is going to prevent their machine learning model from recognizing and processing the image and recognizing the faces of people in the photo. So that's an example of, yes, of like a good application of adversarial examples, in the sense if you care about sort of your privacy and you object to sort of the use of machine learning on your data. How do we trade off? So far we don't have a way to defend against adversarial examples. So we don't have a trade-off yet. Is what I would say, but it is certainly the case that in some cases you might not want to prevent them. So that's a very, very good question. Thank you.
Thank you.
Yep. And so what I wanted to conclude here is that basically now we've made progress as a community. We actually know how to train models that are sort of invariant locally to small perturbations. And so here, this is what you can see here, that the new dotted line, which is the model that we've learned, is now tilted such that for all of the inputs that are within this small disk here, which is essentially a ball of points that are within a small distance of the training image, then essentially all of these images are classified on the same side of the line. So they're all going to be classified as 3s. So this seems like we've made progress. But in practice, we haven't, because we've introduced new vulnerabilities. So let me show you an example where here, this image of a 5 is now an image of a 5 that is very close under the distance metric that we've used to specify the robustness guarantee that we want to achieve with our model. And so the reason why is that the distance we typically use is a p-norm, which does not sort of reflect the underlying semantics of the image problem as we would perceive them as humans. And so what this means is that two images can be very small under this distance, but very far apart semantically. In this case, for instance, the two images are from completely different digits, but yet they have a small distance. And so this new model that is more robust to this class of attacks is going to actually misclassify inputs that the original model did not misclassify. And so this is a very good example where the property that we're trying to achieve for achieving security, which is to have this invariance to small perturbations, is actually directly conflicting with what the underlying machine learning task is trying to do. And so if we try to increase the security according to this definition, we're necessarily going to make the model worse as a predictive model. And so this is sort of a key trade-off that we haven't found a good answer to, because we haven't found the way to specify the robustness in a way that's aligned with the goal of the machine learning model itself. So I see there's another question, so let me take that. This method reminds me of, yeah, I think it is kind of in some ways compression, because you're basically saying all of the points that are within this P norm, so these L people, all of these points are basically reduced to the point in the center of the ball. So this is, yeah, in some ways, this is kind of like compression. And so this is sort of pessimistic in the sense that it sort of begs the question, can we achieve security in machine learning, right? This is sort of a very hard sort of reality. And so at this point, I tried to sort of look at sort of more traditional computer security publications and try to figure out sort of how the community approached this with previous systems before machine learning, with things like operating systems and so on. And what you can find if you read sort of this literature is that very often security needs to balance the cost of protection with the risk of loss. So what this means is you're going to deploy certain defense mechanisms that are going to prevent certain attacks that you estimate will cost you a lot if they do happen. And so what this means is you have this kind of arms race where you're always adapting to attacks that you've identified and you think will have a large consequence on your system. And so this is very much like real world security, where if you have a house, you're trying to prevent burglars from entering your home. So you'll put a lock on your house. It's not going to prevent a bear from entering your home, but this is not some sort of a loss that you put a lot of value on in terms of risk. And so the question that you can ask yourself is machine learning going to result in this same arms race? Where here in this previous slide, what I'm showing you essentially is we find one type of attack. Here on the right, we're able to defend against this type of attack. But if the adversary knows that we're defending in this way, they can find a new attack that will then mislead us again. And so this is obviously not very productive. But fortunately, I believe that machine learning introduces a paradigm that is sufficiently different to traditional computer systems that we can hope to reason about the trustworthy nature of our systems more principally. And so in a more principled approach. And this is what I'm going to illustrate in the second part of the talk with work on privacy. So I'm going to switch gears a little bit and then come back to the security afterwards to compare them. But essentially in privacy, what's amazing is that we've made progress in the technical community in understanding sort of what it means for an algorithm to be private. And this is very interesting because privacy is very subjective. If I ask sort of, usually I say everyone in the room, but I guess everyone in the Zoom call, like everyone would probably have a very different variant of the definition of privacy that they have. And it's very surprising to me that something so subjective has sort of found a very rigorous technical definition. And so the name of this definition is differential privacy. And the idea is you consider an adversary that is observing the outputs of your algorithm. And what you want your algorithm to be doing is producing outputs such that it's impossible for the adversary to tell whether the algorithm was operating on this first database here, which includes the data point for one individual, or if the algorithm was operating on this second database here at the bottom, which did not include the record for that same person. So what this means is if the adversary is looking at your outputs, they can't tell if you, for instance, if you're looking at a machine learning algorithm, they can't tell whether you trained on this person's data or whether you did not train on this person's data. So by definition, they don't even know if the person existed. So they cannot learn any private information about them as a consequence. And so, of course, if you have a strict definition like this, you cannot learn anything about anyone. So you cannot learn any sort of interesting machine learning model. So what you do is you require that these two settings are indistinguishable statistically, which means that you allow for a small leakage of private information, but that leakage is controlled. And so this is what is sort of stated at the bottom here, where you're comparing the probability that the algorithm makes certain outputs on two data sets, D and D prime, which are only different by 1 point, one training record. And you're saying that these probabilities have to be very close, and how close they have to be is specified by this parameter here, epsilon. So when you read differentially private papers, what they'll state usually is the value of epsilon that they're able to achieve. The smaller the value is, the more these two settings are indistinguishable. So the more privacy you have, because it's harder for the adversary to tell whether or not you included this person's data. And you prove this for any possible point in your training set. So any individual that would be included in the data set is protected. So how do we train models with this notion of privacy? There are multiple approaches. I'm going to present one that is called Pate because I worked on it, and also because it makes it easy to get the intuition behind where the privacy comes from. But I recommend looking at other approaches, like DPSGD is also a very popular one that you can find online from my collaborators. So I'm happy to advertise it as well. So here, the idea is you take this data set that you want to protect the privacy of, and you split it in n partitions. So now if my record was in the data set, it's only going to be in one of these partitions. And from each of these partitions, I'm going to train a machine learning model independently. So what this means is I have n models that are all solving the same task, but they were each trained on a different set of data. So they've learned independently from one another. The question is, how do I ask these models to predict while protecting the privacy of this original data set? What I can do is I can ask them to vote. I ask each model, I present them with an input, and I ask them, what label are you predicting? And then I can build a histogram where I count how many votes were received for each possible class, and I output the class that received the most number of votes. This is very intuitive. And you can see that if multiple teachers are making the same prediction, it means that multiple models learned how to make this prediction from different data points, right? Because there is no overlap between these multiple partitions of data. And so this means that you've came to the same conclusion multiple times from different data points. So this is intuitively not something that could leak private information about any of these data points here, which are the inputs to the teacher models, because you could have made the same conclusion without these data points. Okay, and so this provides intuitive privacy. To obtain differential privacy, we need to add one step because there is sort of an edge case where you could still learn private information, which is when basically half of the teachers vote for one class and the other half for a second class. And there you can see that if you have plus or one difference between the two classes, one teacher changing their prediction from one class to the other can change the class that receives the most number of votes, so can change the prediction. And so what we do to prevent leakage of private information in this case, we just introduce noise to the votes. So basically, we're going to randomly flip some of these votes to an arbitrary value, and this is going to prevent these edge cases. And so once we've done that, we have basically what is a differentially private API. We can ask these models for predictions, and they'll respond with a prediction that we know does not leak private information about this data set, or at least it leaks a very tiny amount of private information. And so the main limitation of this approach is that you cannot ask an infinite number of questions to those teachers, because since every single response leaks a tiny amount of private information, if you accumulate over many, many queries, you eventually leak potentially significant amounts of private information. And so what we do is we're using this ensemble to train a student model. So we're basically going to use the knowledge that we've acquired in these N models and transfer it into another model, which is the student model. And so this means that the amount of private information that we're leaking in the worst case will be fixed once we've trained the student model, because that student model will learn how to make predictions by interacting with the teachers, but it will only interact a fixed number of times during its training phase. And then afterwards, we can completely discard all of the information to the left of the dotted line. So we can throw all of this, including the original data. And so one additional advantage of this approach is that you can do this in a distributed fashion. So you could imagine that each teacher here would be a hospital. And so these multiple hospitals would be collaborating together to make predictions without revealing sort of private information that's contained in each of their data sets. And we've actually just published a new result last week where we're able to do this even without sharing any of the models that are involved in the process. So this is sort of a very exciting application where we could imagine looking into healthcare data, but also things like financial data, where you have multiple banks collaborating. You don't want them to sort of share their data or models, but they can still inform one another with predictions from the overall ensemble of models. And so why is this exciting? Why am I spending 10 minutes trying to explain this? The reason is that you can see there is a very strong alignment between having a model that is privacy preserving under this definition and a model that predicts well. Why? Because if you look again at this diagram, you can see that the more the teachers agree together when they're making predictions, the more this prediction is likely to be correct because you've made this prediction multiple times independently. So this is something that is more likely to be a correct generalization from the training set. But it also means that it's more likely to be private because you can introduce a lot of noise to these votes before you change the outcome of the mechanism. And so there's this very exciting synergy between the privacy and the performance of the model, where the more private the model is, the better you would expect that it generalizes from its training data. And so this is very unusual. In security, usually we have to take away some of the performance to provide some guarantees. And here there's some very nice synergy between the two, which is very exciting. Another advantage is that it makes it easy to defend against attacks that we don't know of yet. And so we have very robust guarantees. So whereas this is where I'm calling back to the first part of my presentation on adversarial examples, we had to essentially rely on the fact that we know which attacks we're trying to defend against. And if we didn't know that, then we would basically not be able to provide meaningful guarantees. I'm not going to go into the details here because I'm running a little bit behind on time overall for the presentation. But the point here is that when we train models with differential privacy, we're able to defend against attacks that haven't been released yet. So an example here on the right is this membership inference attack that I discussed at the very beginning of the talk, where based on the model's predictions, we're trying to infer whether a point was included in the training set or not. And so most of the initial attacks in that area, they were relying on the fact that you can access the confidence scores that the model outputs with the labels. So it says, this is a performance is like a sick patient with 80% confidence. And the more confident the prediction is, the more likely it is that this point was actually a training point. And so you can infer the membership based on this. So a lot of people said, well, why don't we just hide the confidence score? And then we won't have to worry about people releasing sort of private information and in particular membership. So the problem with this is that you can come up with an attack that doesn't require the confidence score. In practice, in machine learning, you can estimate how confident the model is by taking the point that you're interested in and perturbing it until you see the model's prediction change. If it takes multiple steps for you to change the prediction of the model, then the more steps it takes, the more confident the model is in making this prediction because you have to perturb the input more before you go on the other side of its decision boundary. And so one of my students basically came up with an attack where he was able to find whether a point was used to train the model or not by only observing the labels. You didn't have to look at the confidence, which means that all of the defenses that were basically specifically tailored at trying to prevent people from inferring membership from the confidence scores are completely unuseful on this attack, and you can evade them. But if we instead use differential privacy, we observe that this is the only way to defend against these attacks that we are introducing that people were not aware of before. And so if people had trained their models with differential privacy, then our attack would not work on their models. And so this is, again, a very nice property of models that are trained with differential privacy. And so this is sort of the first major part of the talk. Now I'm going to go into more recent work. But before I do, basically what we've done in all of the things that I've described so far is we've looked at the training phase of the model and tried to capture definitions of guarantees that we want to achieve in order to align the model with what we would define as human norms, right? So you might define privacy as being a human norm, and if you train your model to be differentially private, you're aligning the model's behavior with what you would expect from a private model, which is to not reveal information that is specific to a specific individual. And so the open problem, of course, is to find definitions for areas where we don't have one. So security is an example where we don't have a good way to defend against adversarial examples, which shows that we don't really know how to specify the sort of intuitive notion as a human that a model is secure. And we also have other additional problems down the road, which is how do we train models that satisfy multiple human norms at the same time? So we have a hard time already training a model that satisfy a specific norm, but training models that satisfy multiple norms is even harder. So for instance, one of my students is looking into the intersection between privacy and fairness, where it's very hard to learn a private model because especially when you have distributions with heavy tails, like in healthcare, where you have patients that you have very few examples of, but they're very important to learn from because these are the cases that you're going to learn how to predict based on. And basically, when you learn with privacy, you are not allowed to learn from examples that you have very few examples of. And so this means you're going to sort of make the performance of the classifier even worse on the tails of the distribution, which unfortunately often coincides with parts of the distribution that will affect your fairness performance, because these might be, for instance, from populations that are not as well represented in the data set. And so this means that as you're training with privacy, you're also introducing another trade-off with fairness. So if you want your model to be fair and private at the same time, it's not currently possible. And so this is sort of an interesting question. How do you deal with this intersection, and how do you trade off between different norms that you would like to achieve? And does that mean that we need to redefine the way that we think about fairness or about privacy? But this is all at training time. So once we've deployed the model and it's making predictions, we also need ways to deal with the failures of sort of our approaches at training time. Because as I just said, we'll never be able to have a model that is perfectly aligned with all of our human norms that we want to capture if we want to have a model that we can trust as humans. So we need mechanisms to be able to tell when we shouldn't be trusting the model, or to fix models once we've identified that they have limitations. And so this is what I'm going to discuss in the last 15 minutes that I have. And so I'm going to skip the first example for the sake of time. I'm just going to say in 10 seconds what the idea is. The idea here is to say, can I figure out which of the points that I'm being presented with I can make predictions on based on the training data that I have access to? And so sometimes what we realize with this approach is that we cannot make a prediction because we don't have the relevant training data. And so we need to abstain from making a prediction. And so this is not something that is straightforward to do with current machine learning approaches, which often assume that the data that you present at test time is going to be from the same distribution than the data that you present at training time. And so that you should respond to all possible queries that you're going to receive once the model is deployed. And so here, this is basically giving a notion of uncertainty in the prediction, where for some of the inputs, we actually don't have the right training data to make a good prediction on. So we shouldn't make any predictions at all. We shouldn't even try to make a prediction. So the problem that I want to discuss, which I think is also very interesting given the agenda of SRI, is the one of model governance, where here, let's say you've identified inputs on which you have limitations of your machine learning model. So this could be, for instance, you realize someone poisoned your data and inserted points that you shouldn't have trained on. Or someone brings up some of the legislation around privacy and says, I would like to delete my data. So now we know that models can potentially memorize this training data. So when a user comes to you and says, I want to delete my data, you basically have to delete the model that you trained on this data, any model that you train on this data. Otherwise, you risk that this data will eventually leak through the model indirectly. And so this begs the question of, can we do the opposite of machine learning? And can we unlearn what we've learned? So this is sort of, we call this machine unlearning, where you're trying to take a model and then produce another model that you could have obtained without that training point that you're trying to delete. And so this is a very interesting question. It's very hard. You can't solve it with differentially privacy. So I'm a very strong advocate of differential privacy. So for once, differential privacy does not solve the problem, because here what you would have to do is make it so that the contribution of a training example is 0, which in differential privacy, you never make it 0, you make it small and bounded, but you never make it 0. So this is not a good fit. And it's very hard because the way we train machine learning models, sort of modern machine learning models, introduces a lot of randomness. So stochasticity in the algorithms, the way that we analyze the data is sort of in a shuffled order. And once you apply the updates to the model to find sort of the right parameters to make good predictions, you can't sort of go back in time easily. And so the definition that we came up with is to say that we obtain a distribution of models. So the possible models that we obtain if we learn and then unlearn should be the same than the models that we obtained without learning on that point in the first place. So imagine you have my data is included in the training set. The company trains on this data set with my data and then unlearns. They need to be able to prove to me that they could have obtained the model that they have at the end of the process once they've unlearned in the first place without training at all on my data point. And so this is a very strong definition because intuitively you can see as an individual, this is what I want, right? I'm deleting my data. I want your models to basically be such that if you had never seen my data, you would have obtained the same models. But technically speaking, this is a very difficult problem because, again, it's very hard to trace back the contribution of one single training example to the different parameters that your model has learned. Yeah, so the thing is, if we use differential privacy, so to restate this, we'll basically show that essentially the model has a bound on the value of epsilon that I showed in this slide, which means that it can learn from each training example only if it's smaller than a certain amount. And so the amount of information that you can extract from each possible training example is bounded, but it's never 0. Because otherwise, if you had sort of set this bound epsilon to 0, you wouldn't be able to learn from any training example. So your model would be complete useless. You couldn't learn anything. And so that's why the differential privacy definition doesn't hold, because it holds for any possible point. Whereas here, we only want to unlearn specific points. We want to unlearn a handful of points from the training distribution. So hopefully that clarifies. And so the idea that we put forward is kind of similar to the Pate framework that I explained before, where you first want to split the data in multiple partitions, which means you're going to train smaller models rather than a big model. And what this means is when someone asks you to delete the data, you only have to update one of the small models instead of updating the large model. So this makes it more computationally efficient because it decreases the amount of computation you need to do in order to compute the gradients of the model. The other change that we introduce is that we change the order in which the training algorithm sees the data, and it exploits the checkpointing mechanisms that people use commonly in the industry, which is just the idea that you're going to save intermediate states of your model throughout training. And so what we're doing here is we're saying, let's change the order in which we present the data points. And we gradually introduce the data rather than having the model take a full pass on the entire data set at each epoch, which is each step of the training algorithm. And so what this means is that you can imagine if you have sort of a whole training set, you're going to first train on 10% of the data for a while, and then save a checkpoint with the model parameter states. And then you're going to insert 10% additional data and train on 20%, save another checkpoint. And then if you keep doing this until you've seen the entire data set, when someone comes to you and say, you need to unlearn my point, you can find the last checkpoint that you've saved before introducing the corresponding piece of data. And then you can resume training from that checkpoint. So that means that rather than start from scratch, you're potentially saving a fraction of your training cost. And so you can retrain the model faster. And so eventually, so this is sort of the way that we approached it. And it introduces very interesting questions, again, with societal implications. For instance, the way that you partition the data can be based on a priori information you may have about who is more likely to unlearn their data set. So for instance, some countries are very sensitive to privacy questions. For instance, Germany is well known for being very sensitive to privacy. So you could imagine you would put all the German users in one partition because you know you're going to get a lot of unlearning requests. And so this is going to save you a lot of compute. But then you could argue that this might be unfair to German users, which because it might degrade the performance of the model on their data. And so there's, again, an interesting trade-off between the fairness and here the unlearning property that we're trying to provide, which I think would be great to sort of work on if people are interested. Okay, and so the last thing I want to talk about, and I guess I have 6 minutes, is the problem of deepfakes. So here, I guess, thanks to the political news, I don't have to motivate why we should care about deepfakes. I just want to say that this is an old problem. Back in sort of the times where people were writing letters, people were already forging letters to make people say things that they didn't want to say. Like I think there was an example with Washington saying that he didn't want to fight the British or something along these lines. So the progress that we've made in machine learning, especially with generative adversarial networks, only makes it easier to perturb media, and in particular images and videos, which were previously thought to be a little hard to modify. And so as computer scientists, what is our default reaction to this? We're going to come up with technology to fight this technology problem, okay? And so one example we could follow is to say, deepfakes typically have artifacts in the videos that you can identify as a human. For instance, there are issues with the way that the body movement is synthesized, where you can see it's not really, it doesn't look natural. And so you can train a model to detect these artifacts. But then this is not really a long-term solution, because the very way that these deepfakes are created is by training one model that is generating the deepfake to be opposed to another model, which is called a discriminator, which is trying to tell whether the image is fake or not, in order to help the model that is synthesizing the images to produce more realistic images. And so any sort of progress we make from a technical standpoint at detecting deepfakes is only a short-term win. And in the long term, all we're doing is making it easier for malicious users to make better deepfakes that are harder to detect. And so this is sort of a fundamental flaw. And there's a lot of work going on in trying to detect deepfakes. And in the long run, there's no way that it's going to sort of improve the situation with synthetic content. And it's very much like the problem with antivirus software on computers, where you can come up with a signature for malware that you know of today, but this doesn't mean that you can detect new forms of malware in the future. And so here, my call to action is that we need, in addition to sort of the computer science approach, we also need help from the policy end of things. Right, so we could imagine legislation that would establish criminal penalties and sort of put sort of more guidelines around the platforms to have clear publishing principles to make it clear what is a deepfake, what is not a deepfake. And of course, we're at a university, so we can also imagine the role that education can play where, for instance, in my Intro to ML class, I like to teach students for just a few slides about sort of the security, the privacy, the fairness implications of machine learning, and just being able to be aware of these problems, I think can help you when you're then an engineer in a company and you're about to create one of these machine learning systems. Is it really worth sort of the benefit that I'm thinking it's going to provide? Is it going to be something that I have to trade off with potentially negative consequences for society? So I think we really need sort of a more comprehensive approach, and we won't be able to sort of solve this purely technically speaking. And deepfakes is a very good example of why. And I'm going to skip this. I'm just going to conclude to say basically what I wanted to convey in this talk is that there's a whole class of approaches which at training time when the models are being designed, basically the goal is to align the model's performance with human norms. And then at test time, we need to be able to manage the failures of our machine learning systems. So this is the whole idea of model governance, and there is very little work on this at this point. So things like machine unlearning basically allow us to patch existing models, and so to make their life cycle sort of more interesting to society. And then of course, beyond technology, I just mentioned legal frameworks and other types of policy actions I think are very important. With this, I want to conclude on an optimistic note. So as I showed in the privacy part of the presentation, trustworthy ML is an opportunity to make machine learning better. So we can make models that generalize better, which is sort of the holy grail of the machine learning community, by looking at sort of how trustworthy they are. And then you mentioned in the introduction the two libraries that we're working on. We've actually moved the URL, but I think this still works. It will redirect you, but CleverHunts and TensorFlow Privacy are good starting points if you want to play in the space. Okay, I think that's it. So I'll take any additional questions, or people can also email me if we're out of time.
Great, thank you, Nicolas. That's terrific. Should we stop the share? We can
Sure.
See everybody. Super. Let me first go to Elliot Krieger, who's one of our graduate fellows.
So yeah, I just was a little unclear on the unlearning approach. So there's two questions. One is, what is happening within a partition if one person's data is unlearned? Is all of that data discarded? Is it somehow like recombined with the checkpoints? And then just to quickly say the second question is the guarantee on like the model you arrive at with or without that person's data. Is it about the model parameters in the parameter space or the predictive distribution?
So it's the model parameter space for the second question. And for the first question, the idea is that if you have a partition of someone's data, so we have two notions of partitioning. We have the sharding, which is just you partition the initial data set. And then we have slicing, which is in each of these shards, you're further dividing the shard into smaller chunks. And so what happens is that when someone wants to unlearn their data points, they're in one shard, and within that shard, they're in one slice. So that's basically how this works. And so what this means is two things. When we want to unlearn the point, we first need to revert to the checkpoint that was saved before introducing the slice that contains the data point to be unlearned. And then we need to retrain the model starting from this checkpoint on the rest of the partitions, on the rest of the shards data. So basically on the remaining slices without the point. So this means that rather than retraining on the entire data set, you're decreasing sort of through the sharding, you're decreasing the amount of parameters that you need to update because you're now updating smaller models. And then through the slicing, you're decreasing the number of training iterations that you need to go through because you're basically decreasing the number of epochs that you have to go through and the amount of data that you have to process.
And so in your experiments, just to follow up on that, like how many data points are you unlearning at once? Because it seems like that what you're talking about seems very sensible for unlearning a handful of data points, but at a certain point, just the number of like possible checkpoints is going to kind of explode.
Yeah, so basically the number of checkpoints is basically trading off with storage. So the more storage you spend, of course, the more retraining gains you're getting. And we can only unlearn basically a handful of queries at the same time. So I think in the paper, we give examples of the numerical speedups that we get in the introduction. And it's for a couple of dozens of unlearning requests. So basically what we looked at is sort of, if you look online, you can find data that, for instance, they released about search engines, like the ratio of unlearning requests that they get based on sort of the number of queries or so on that they have to process. And it's a very small fraction of the data. So basically what we checked is that the number of queries that we're able to handle is sort of is larger than the regime that they're sort of reporting is typically what people would ask to unlearn. But yeah, you're absolutely right. The idea is really that we can unlearn sort of faster, because of course, if you want to unlearn sort of a large chunk of queries, you might as well just retrain the model from scratch at some point. This will be sort of more efficient. Yeah. Thanks.
Great, thanks very much. Lisa.
Hey, Nicola, this was super interesting. So I was happy to see the last slide mentioning law, because as you know, you're one of my favorite tech people to talk about tech and law with. And
I should say that I don't put this slide just because I'm talking to this group. I always have this slide, like wherever I go in I guess in the Zoom world.
That's fantastic. Yeah, so I guess I have a kind of general comment and then a more specific kind of example in relation to the machine unlearning. And so there's one way to interpret kind of what work law can do, which is we want to start with strong technical solutions, and when those technical solutions are frail, we sort of shore them up with law. But there's another way to think about it, which is, if you want to create these trustworthy symptoms, we have a whole set of tools at our disposal. Some of them are law, some of them are technical, some of them might be, social in other ways. Some of them might be around, business models, et cetera. There's a whole set of factors. And I was thinking about this in relation to the example you gave with that. I love that slide with the bear on the railing. You lock your house in order to sort of prevent people from coming in, but not everyone locks their house, right? So in some communities, you have cultural norms and people just don't go in each other's houses, or neighbors look after each other, or you have strong laws and the laws are strongly enforced, where it's a crime, not just a trespass. Then you don't necessarily need to lock, and the more you need to lock and the stronger the lock has to be is where you have sort of the societal breakdowns or the lack of legal supports, and where those are stronger, you might not need the technical solution at all. And so I'm kind of wondering how that might work out in kind of the thinking about machine learning. So I was thinking about this in relation to your example about machine unlearning. And it'd be interesting to talk about this in more detail. But so in Canada, for example, in data protection law, like the new introduced legislation, we'll see if it passes federally, introduces a right of data deletion. We don't have a clear right of data deletion currently. There's one that's being introduced, but it's not clear to me that you necessarily would have this ability to ask for the machine unlearning, because there's ways around it. So for example, there's a provision that says you can have reasonable contractual terms that say, you're not going to allow someone to delete their personal information. And you can imagine, I can imagine anyway, a regulator saying, well, where you have reasonable contractual terms, what might those be? Well, where you're using strong differential privacy to train a model, and you're not doing anything socially harmful with that model. You're not using it to like oppress people in some way, right? So we say in those set of conditions, that's reasonable, and actually you don't have a right of data deletion, and we don't have the problem of machine unlearning, and we don't need the technical solution. That doesn't seem crazy to me, and I just kind of wonder, how do we think about what work these different aspects should be doing in creating a universe of trustworthy machine learning?
Yeah, I think that makes complete sense, that if you know that, for instance, someone is using differential privacy, then you might not place sort of strong requirements of being able to unlearn data points. It's not sort of the same guarantee, but it makes sense that if you know that there is sort of strong privacy preserving practices happening around this machine learning system, that the consequences that you're trying to mitigate sort of through unlearning are not sort of as strong in this case. One thing that I find is sort of potentially risky is that there's a lot of reusing of models. So there's a lot of results where you do transfer learning, where you take a model, train it for one particular application that you have in mind, and then you reuse this model as a starting point to build a second model on a completely different task that may have like no relationship, at least apparently whatsoever. And so this makes it difficult for me when we have these definitions where it sort of assumes sort of good intent, because sometimes you might legitimately not know what you're going to use the model for down the road. So this might be a little bit tricky. Maybe we could have like a provision that says you can't reuse the model beyond just having it predict for the particular task that it was trained for.
Great. So I have a bunch of questions. Please, others, feel free to raise your hands, and I will pick those up. Nicola, I was wondering about the actually it's a connection between the first part of your talk and the adversarial attacks and differential privacy. So I think your presentation was the first one that made it just so crisply clear to me that differential privacy is really focusing on, what can you discover from having some access to the model, maybe just the predictions of the model. So separate from access to data sets. So, we spent a lot of time thinking about how we're going to share data and aggregate the data for training. And this is really about what we can find from the model. But
the definition is really looking at the algorithm specifically and not the data set itself.
Right. And I'm thinking about this for a while. And for the first time, that was just like super clear. That's very helpful. So what I want to think about, it's sort of related to Lisa's question, is, so to what extent is differential privacy a solution only to very deliberate, one would say malicious efforts to take predictions of the model or access to an API or something and read back and say, oh, this person was in the data, or actually I can interpolate what their actual data was in the data set. Because that sounds like malicious adversarial behavior. And so that then becomes part of, okay, so what kinds of efforts do we want to take to protect against that? Lisa talks about what if we live in a community where we just say, no, people don't try and walk into your house, so we don't need to have so I guess I haven't got a clear idea of, so to what extent is it malicious adversarial behavior? And then what do we know about the domain, the scope of that?
Yeah, so right? I think I understand where your question is getting at, and basically the guarantee that differential privacy is providing is very sort of pessimistic. The way that I like to think about it is that it assumes that we already lost all of our privacy, and so we're just trying to not make things worse by releasing new analysis and new algorithms that are using our data. And so basically you're trying to make sure that whatever delta of private information that you're going to leak in addition to what's already out there is not going to be significant. And so this is one of the reasons why the guarantee is so interesting, because it means that whatever the adversary comes to know in the future is not going to affect the guarantee that you're able to prove right now in the present. And so I think this is sort of getting at what you were asking, which is sort of, it's very pessimistic, and it's a worst case guarantee. So it assumes sort of the adversary has sort of the adversary that I showed on the slide, in some sense, has a lot of control over the inputs to your algorithm and sort of how it can query your algorithm and so on. But what this means as a consequence is that you can sort of deploy your model and sort of sleep well at night, because you know that sort of no matter sort of how much access the adversary has to, for instance, auxiliary data about the individuals involved in your model, then it's not going to improve sort of their ability to leak information. That said, perhaps there are settings where we can say we're able to sort of operate in a different setting, where now we know that we have very constrained access to the model, and we're willing to sort of maybe use some legal tools to restrict sort of what people can do with the model's predictions. And at that case, we might be able to sort of loosen up our requirement on the differential privacy bound that we're trying to prove. And so this is a little, so if you discuss this with people from computer security, they will be sort of usually sort of allergic to these types of ideas, because it's sort of exactly what the definition is trying not to do, which is to sort of make assumptions about what is possible for the adversary, because this is what leads to the arms race that I was discussing in the other part of the presentation. That said, what we're trying to do, so we actually have some recent results on this. We're trying to basically instantiate the adversary in practice, because originally it's a very theoretical adversary. It's kind of a conceptual adversary that you're using to sort of analyze the algorithm. And so now we're getting to a point where we can say, like, here's an algorithm for training my model with privacy, with differential privacy. And so how much in practice can I really leak from the model at different sort of bounds that I'm able to prove in terms of differential privacy? So depending on how strong the sort of theoretical guarantee is, how much can I actually in practice exploit and leak private information from the model? And so we found that actually the bound is tight. So that means if you actually give all of the sort of unrealistic capabilities that the adversary is assumed to be able to have, then the adversary can actually leak as much information as the theory actually states. And so the question then is, what are the types of assumptions that you want to make about what the adversary can and cannot do? And then based on that, you can sort of modulate the guarantee that you're shooting for. But again, this is sort of a difficult exercise. And in practice, I think most of the times practitioners don't really deal with this very honest, like it's not very transparent how people set their privacy budgets. And so I think this is sort of related to this, that it's really hard to interpret what the budget means. And so you can't really say, like, here is like you need epsilon to be smaller than this value, and then you're good to go. This is something that's not really easy to do.
Right. Well, that's just related to, just to follow up on that. So I certainly hear some people say, look, differential privacy is still in the realm of theory. It's not something that's very practical for us to deploy at scale. Is that accurate? What gives that impression?
I think actually it's easier to deploy differential privacy when you have lots of data, because you get inherent privacy from the fact that you're learning sort of this task from like billions of records compared to learning from tens of thousands of records. Because each record you can see intuitively has sort of less of a contribution to the same model. And I think one issue is, so there are two issues. One is compute. So depending on the implementation of the differentially private learning algorithm, it can sort of oppose some of the parallelism that has helped sort of scale up the training of machine learning models on very large data sets. So actually, Elliot was working on an implementation that is very efficient because it's able to parallelize similarly to a non-private algorithm. And then there's another issue, is that because the performance is harder to achieve on the tails of the distribution, what this means is if you look at sort of the raw benchmark numbers, typically the accuracy of the private model will be lower than the non-private model. But the question there I asked is, what does it mean really for that non-private model to have such a high accuracy? And what I would argue is that the non-private model is actually just memorizing all of these corner cases that you don't have enough training examples of. And then it's just spitting out the same prediction at test time when you present it with an example that is very similar. And so this means in some sense, and we've done some preliminary sort of experimental work to show that, essentially the extra points that you're missing in some cases of performance, they're probably performance that you don't want to have in the first place, because it just means your algorithm is just memorizing some of its training data. Of course, there is sort of a gap in the performance that I think we should be able to overcome with sort of better techniques for learning with privacy. But definitely there's sort of a portion of the performance that we're losing that I think we shouldn't aim to gain it back. And so, but that's very hard, right? If you talk to a production team in a company, it's very hard to justify sort of why would you give up this performance gain that perhaps they've spent 3-4 years and potentially millions of dollars to try and improve sort of the accuracy of the model. And now you're saying, but this model performs better, it's more private, it generalizes better, but it's not going to reflect in sort of the metric, the benchmark metric that they're using to track performance. So this also asks the question, sort of very philosophical question in machine learning. What does it mean for a machine learning model to be a good machine learning model? How do you measure performance? And this is something I think that in a lot of cases we're realizing we don't have very good ways to measure beyond sort of the toy settings that the community started. Now that we're doing so well, you see things like fairness, things like privacy, things like security. They all show that sort of the traditional metrics you're looking at don't really capture the sort of the performance in general of the model that you would need to be able to trust it.
Right, right. Yeah, I wonder if that's not even say, because we don't tend to, these are technical conversations and they're not, you know, as expanded yet in sort of the policy and legal domains, and even use of the word private, right, to say it is private or it's not, as to say, well, no, what we really are doing is we're setting a slider somewhere, right, and that's actually a political determination or a legal determination about, okay, what probability do we tolerate, what is appropriate levels of, and without the, you know, the bank as your example, without sort of an external metric that's saying, here's what you're supposed to be reaching for. They're saying, well, why would we incur this cost on accuracy?
Right, and even what it means sort of to be private, like we're having discussions that never end with Lisa, David, and Sesho about what is privacy, and it's like they're like very different perspectives, and sort of even just the word private means very different things to different computer science communities. So if you talk to a cryptographer, they mean by private sort of confidentiality, which is even different from sort of the private that I discussed today, which is differentially private. So it's very interesting, sort of the plurality of the definitions that fall under the English word private.
Right, right. Any other questions? I have another direction to go if somebody, oh yes, Benjamin, I see your hand, a real life hand.
I can't figure out how to do the other one, but yeah, so the question going back to the adversarial examples, just trying to, I guess, understand a little bit about how they work, because I was wondering if this has anything to do, or if it relates to the kind of talk about like explainable models or interpretable models, because it feels like part of what's going on, like the reason why humans can't detect the changes, but it's flipping the model, is that the model isn't sort of intuitively, it's not looking at what humans would look at. It's not looking at the patterns we would expect. And in fact, we don't know what the patterns are. That's why we can't determine why it is that changing these few little pixels changes the outcome.
Yeah.
So is that a direction anyone goes for trying to fix it, of trying to like force the models to be more generalized on more like the patterns that we might expect humans to be picking up on?
Right. So there are some results that are sort of showing that some of the vulnerabilities are explained by the fact that you're relying on different features, as you said, as humans, compared to sort of what the model is picking up on. And there's sort of this whole criticism of, is the model just picking up on correlations that you find sort of in the training data that help you sort of distinguish the different classes. As far as the connection with interpretability is concerned, this is very valid. And in fact, the way I would put it is that the reason that the models are easy to attack is the reason that they're easy to train. So why can you train a deep neural network? Because it's easy to sort of differentiate it and compute gradients of its sort of outputs with respect to the parameters. And because you can do that, you can also compute gradients of the outputs with respect to the inputs, and then find perturbations of the inputs that will force the changes in the output. Whereas in the training, you would have tried to find perturbations of the parameters that would change the output in a way that it improves your, sort of your objective that you're trying to minimize. And so there, like, clearly there's a connection, like the technique that I introduced after sort of like writing this paper out, I discovered also like a couple of months later, the whole like field of looking at gradients to understand sort of what a model is predicting based on. And you can see there's lots of parallels. The term saliency comes up in both areas, and it's definitely the same underlying intuition for sure. But then the question that I have, which is sort of very high level, is what does it mean for a model to be interpretable? So this is something that I still don't have a good answer to. And I feel like if we can't solve a problem by writing sort of a traditional computer program, and so we're using a machine learning model to instead solve this problem, why would we expect that we understand what the sort of the machine learning algorithm is going to come up with to solve this problem if we were not able to solve the problem ourselves? And so like this is something that I always sort of wonder. It's more of a very high level discussion, but I like to ask this in my interviews. It's a fun question to like think about. And it's not clear. Like I don't know what the right answer is. You can imagine sort of there's some research that's constraining models to use abstractions that are more easy to understand by humans. And so there's sort of this argument that's made, sort of a decision tree is easier to understand, but then my counterpoint is if you have a small neural network, it's just as easy to understand as a decision tree. It's multiplying values, summing them up, and then passing them to the next neuron. It's very easy to understand. And the decision tree is only easy to understand if it's small. And so you can also ask yourself sort of in practice, if you have a realistic machine learning task, it's going to be not one tree, but also like a forest of many trees. And so then is it really interpretable anymore? I'm not sure, to be honest. And then you can also sort of imagine that you're trying to sort of get some insights as to sort of visualize what is going on in the model, but then it's always unclear sort of how accurate that visualization is compared to what the logic is really underlying this model. And yeah, I think it's very important. Like there's lots of applications where unfortunately people will not sort of use machine learning algorithms unless they sort of can pinpoint the precise logic under it. And so it's sort of a very strong limitation of the current approaches.
That's great, and I you know, you also mentioned sort of these tensions between so that's attention, privacy, and thinking about interpretability. Also, the one you mentioned before about fairness and privacy and learning on smaller parts of a data set, which I think is something really intriguing to explore in thinking about fairness. And I think part of that conversation needs to you know, it needs an interdisciplinary group, right? Something like what we have here, and Ron is mentioning connections to robustness as well. Yep. So that's a great set of conversations to have. So Nicolas, thank you so much for a terrific talk, and
thanks for having me. It was a great audience with plenty of questions.
Yeah, and we love having you in the community. I'm just going to add, there was a question in the chat about the just so that everybody knows, if you're new to us, that we meet weekly, and if you'd like to make sure you're getting notification of the weekly talk, please reach out to Jacqueline Ho, and we have been recording, and so the recording will also be made available on our website. I think usually with the slides as well when appropriate. Is that right, Jack?
The slides, no problem.
Great. Wonderful. So we'll do that. So next week, very excited to have Avery Slater giving our talk, one of our faculty affiliates, on latent traits, AI, and the new psychometrics, which sounds really intriguing. I'm really looking forward to that, Avery. So take care, everybody. Have a great rest of the week, and we'll see you next Wednesday. Take care. Thanks again, Nicolas.
Thank you.